Okay, let's look at uses of capacitors. Capacitors can store a charge. Okay, electrolytic capacitors mainly will be used for storing a charge. Capacitor charges up. This plate charges to the positive. This plate remains at the negative. Okay, so it will hold a charge for a certain period of time, depending on how large that capacitor is. They're used in timing circuits, okay, for timing purposes. They block DC or direct current, and they will pass AC or alternating current. Used in filter circuits, okay. Now, let's look at each one of those situations. Okay, capacitors storing a charge. As we mentioned earlier, when you place a capacitor across a supply rail, okay, 0 volts down here and 12 volts here, the capacitor, the positive side of the electrolytic capacitor will charge up to 12 volts. The negative will stay at 0 volts. So we will attain a 12 volt charge across the capacitor. Now, once we disconnect that voltage, okay, so I've got a switch here. This is a switch. All right, switch 1, okay, switch 1 right there, allowing current to flow down through the capacitor to charge it up quickly, okay. And once it's interesting, once the capacitor is charged up, as you saw on the curve before, the current flow slows down and then stops, okay. It's only an alternating current that will basically allow the cap to charge. Okay, so it's a spike. It's a spike in current. Okay, it races up to 12 volts, but then once it hits that 12 volts, it stops. It blocks DC at that point. Okay, so if we were to take our switch, right, like that, that's our switch. Okay, we just put it midpoint here. Okay, so it's no longer connecting the cap to the 12 volt rail. Our capacitor is holding 12 volts across it with a large charge, okay, doing nothing at the moment, just sitting in air, okay, nothing at all. Then we take our switch and we connect it to a camera flash bulb, like that. All of a sudden, the capacitor will discharge back through the flash. It will lose its charge. 12 volts across it will discharge back through. Now the rate of discharge, you saw before that it charged at 0.68, 0.86, blah blah blah. Well, it will discharge also at the same rate, but this time the resistance will be the resistance of the flash bulb itself, which will dictate what the time constant is of that discharge rate. It'll be very, very low ohms, extremely low ohms. Light bulbs generally are, flash bulbs generally low. Flash, and then the capacitor is discharged. Okay, here we have capacitors used for timing. Now I've changed the circuit a little bit, but let's work with it. Okay, we have a 2 volt power rail, okay, positive 2 volts here and 0 volts running along the bottom. We have a series circuit of a 100 ohm resistor coming down to make a 20,000 microfarad cap. That's a pretty big cap, by the way, okay. Probably impractical for what we're doing, but to explain the circuit to make it work. They're the values that I've picked. You'll see why in a second. Okay, so what does this circuit do? After 10 seconds, this circuit turns on an LED. I haven't explained these yet. They're a form of semiconductor. They're a diode that emits light, hence light emitting diode, LED. Now, it takes 2 volts across it at a current of 20 milliamps through it to turn the LED on. Now, 10 seconds, we want to turn that on. So we have to pick our time constant to allow after 10 seconds to turn the LED on. Going back to our charge rate for capacitors, we know that they charge at 0.68, 0.86, 0.95, 0.98. So 100% charge, 2 volts, we want that to equal 10 seconds. So if there's 5 time constants to fully charged, one of those time constants must equal 2 seconds. So 100 ohms times 20,000 microfarad, 2 seconds. Okay, you may ask why I've picked a rather large capacitance value. The reason is this: at 2 volts, I want to limit my current through the LED to 20 milliamps. Okay, any more I risk burning the LED out. Getting back to Ohm's law, 2 volts. Okay, across here will give us 2 volts divided by 100 will give us maximum amount of current flow to be 20 milliamps. Okay, it'll actually probably be a little bit less because we have to look at the resistance of the LED because that is in series with the 100 ohm resistor. But in a perfect circuit where the LED had no resistance, okay, we'd be saying that we're limiting the current flow through the resistor to 20 milliamps via a 100 ohm resistor. But this will have a resistance, so this will drop down. Whereas the resistance of the LED plus R will equal 100 ohms total, minimizing the current flow to 20 milliamps. Okay, so after 10 seconds or 5 time constants, this point equals 2 volts. Then it rises up. After 2 seconds, it's 1.36. After 4 seconds, it's 1.72 volts. After 6 seconds, it's 1.9 volts. After 8 seconds, it's 1.96 volts. And after 10 seconds, it's 2 volts. Now, you may say, what good is that? Why do we want to just turn on an LED after 10 seconds? Alright, over here we have what's called an optocoupler. Let me clean this up first. Get rid of that, it's been bothering me. Okay, yeah, that's better. Okay, here we have an optocoupler. It's a 4-pin device, 2 input pins, okay, which is supplied to an, yeah, you guessed it, an LED. And then we have a gap between the LED and what we call a phototransistor. So, phototransistor turns on when the LED turns on. Okay, light passes across, hits the phototransistor and turns the transistor on. Haven't covered transistors yet, they're a form of switch, but we'll get to that in a while. Okay, so after 10 seconds, our LED turns on, our phototransistor goes short circuit or on, supplying 12 volts through a relay coil down to 0 volts, okay, charging the relay up, which then turns the relay contacts on, supplying power to a 12 volt siren. Okay, so after 10 seconds, LED turns on, phototransistor turns on, relay turns on, supplying 12 volts to a 12 volt siren. Simple timing circuit. All right. Yeah. The annual meeting's on, up in heaven. God's overseeing it all, and Jesus is there with the apostles. They're having a coldie. Anyway, God raises the issue. Any topics? It's a topic for the meeting. And Jesus says, we've got to pop in on earth. You know, the drug epidemic down there is just running rife. God says, what do you think we should do, Jesus? And Jesus sort of scratches his head. Anyway, there's talk between the apostles, rhubarb. Anyway, John, he puts his hand up. He says, Lord, yes, John. He says, I have a suggestion. Why don't I take a few of the boys down and we'll go and grab some samples and see what all this drug rubbish is about before we make a decision. Jesus, he looks and he thinks, yeah, I can see merit in that. Okay. Mark, Matthew, John. Yes, Judas, front and centre. Anyway, they all front up. And he says, yeah, 1 week to go down, collect a sample, be back here within the week. Anyway, about 3 days goes past, there's a knock at the door. Jesus says, who is it? It's me, boss, it's Mark. Good. What did you get, Mark? What did you bring? He says, I bought cocaine from Bolivia, boss. So anyway, lets him in. Another day goes past, there's a knock at the door. Who is it? Boss, it's me, Matthew. He opens the door and he says, what did you bring, Matthew? And he says, I bought crack from New York, boss. He says, come in. Anyway, another day goes past, there's a knock at the door. Who is it? Boss, it's me, John. He opens the door and he says, what you get, John? What you bring? He says, I bought marijuana from Colombia. He says, good cake. Anyway, about half an hour later, there's a knock at the door and he says, Jesus says, who is it? He says, it's me, boss, it's Judas. He opens the door and he says, what did you bring? And the guy pops out and he says, freeze, it's a drug squad. You don't know. Anyway.